In the previous lecture, we developed the constitutive equation for thermo-elasticity for homogeneous linear isotropic media. And we saw that it makes sense to put the stress as a function of the stiffness matrix times the strain plus another term that corresponds to temperature, where beta is the linear thermal dilation coefficient, K is the bulk modulus of the isotropic solid, and theta is the change of temperature. In this video now we're going to expand, well, not really expand, but use this equation in order to obtain what will be the thermal stress under uniaxial strain condition, which is closer what it occurs on surface. For that, let's imagine the following case in which we have the injection of a cold fluid into a reservoir that has a large permeability so that the changes of pressure are relatively small. We're going to use this assumption in order to assume that the changes of effective vertical stress are negligible. As we know, in this condition also we assume that the total vertical stress is going to remain constant. And for the uniaxial strain condition, also we assume that there is no change of horizontal strain anywhere. And that's also similar to assume that the cooling in all these reservoir layers is going to be uniform. As we said before, this reservoir is very permeable and we're assuming a long-term injection, so the change of temperature occurs everywhere in this formation. All right, so let's go ahead and work on this equation in order to find what is going to be the expected change of stress due to the change of temperature. The first thing that we're going to do is to write the stresses as a function of strains and plus the thermal component. And for that, I'm going to write the components of the stress tensor starting by the normal components. And I'm going to disregard the shear components because those are not going to change as long as, or not, those are not going to have any value as long as the change of temperature and the change of pressure is the same everywhere. So by doing that, I'm just going to use the top left part of the stiffness matrix, where the stiffness matrix is equal to the following for the normal components. We have here a common factor, and over here we have just elements which are a function of the Poisson ratio. And of course, this is a symmetric matrix. This is going to be multiplied times the strains that corresponds to the stresses, and I'm going to add here the thermal component, which is the same in all directions. All right. The next step is going to be to use our boundary conditions so that we can solve for the parameters that we want. Since the horizontal strains are 0, then I can cancel these two terms, and I can obtain equations for sigma 11 and sigma 33 as a function of epsilon 33 and as a function of the change of temperature. So for example, let's start with sigma 11. Sigma 11 as given by the top equation, since these are going to be equal to 0, it's just going to be the product of this one times that one times this one plus that. So let me write that and bring the Poisson ratio here to the top. So this is going to be the first row times the column vector, and this is times epsilon 33 plus 3 beta k theta. All right. next step, we're going also to find an equation for sigma 33, and the idea is just not to use here epsilon 33, but rather to use sigma 33. This is a similar step to what we did in pore elasticity. All right, so now in order to get sigma 33, I need to multiply the third row times a column vector, and therefore I'm going to obtain the following. Times epsilon 33 plus 3 beta k theta. And let me now use this equation in order to replace the epsilon 33, which is over here, by a sigma 33. And the result is going to be the following. So sigma 11, same equation that I have above. This is the part that depends on the Poisson ratio and Young modulus, and epsilon 33 in this case is going to be sigma 33 minus 3 beta k theta multiply 1 plus Poisson ratio 1 minus 2 times Poisson ratio divided what was in the numerator, and this times sigma 33 minus 3 beta k theta, which is what I get from that equation. And this is going to be plus 3 beta k theta. Okay, so fortunately here we can do quite a bit of elimination, because the Young modulus is here, the Young modulus is here. This denominator is also in the numerator. So at the end of the day, what I'm going to have is just a lot less than what I have on top. So let me go ahead and write the reduced form of this equation. So I have here the Poisson ratio divided 1 minus Poisson ratio sigma 33, and also I can use as a common factor 3 beta k, and in front 3 beta k theta, and in front I'm going to have here Poisson ratio divided 1 minus Poisson ratio, and this is going to be negative. So let me put it over here, and this is just going to be equal to 1, the common factor for that. And therefore, what I'm going to obtain here is, let me complete the equation, sigma 11 is going to be equal to the, hopefully you remember this one, it's a effective stress coefficient of horizontal stress for linear elasticity. And here, let me add this, and this is going to be 1 minus 2 Poisson ratios, adding these two terms, 3 beta k theta. Okay, so this is our equation, and now with this equation I can tell what is going to be the horizontal stress as a function of the effective vertical stress, and also as a function of the change of temperature and also the properties of the rock, beta and k. And let's try to explore what we are most interested in this particular case, which would be what is going to be the variation of effective horizontal stress due to a variation in temperature, which mathematically it's written as the equation I have over here. And I'm going to assume that the temperature is not changing the effective vertical stress, and also the pressures that I use for injecting are not affecting the effective vertical stress. That will be true as long as those changes of pressure are small. And as a result, what I'm going to have is just a derivative of this with respect to theta, which is just going to be equal to 1 minus 2 Poisson ratio, 1 minus Poisson ratio, 3 beta k. And this is not the end of the formulation here, because we can also use, to avoid confusion, let me put all of these between parentheses. We're going to use the equivalency of the bulk modulus in terms of the Young modulus and the Poisson ratio. The bulk modulus can be written as the Young modulus divided 3 times 1 minus 2 Poisson ratio times beta, and I forgot the 3, times 3 and times beta. So this one is K. And this is just a property of isotropic media for linear elasticity. All right, so now that I have that, you can see that I can further simplify the equation. And this is just going to be, let's get rid of this, let's get rid of that. I have a 3 here, I have a 3 there, and the answer for my question, what is going to be the change of effective horizontal stress caused by the change of temperature, is going to be beta times the Young modulus divided 1 minus Poisson ratio. Let's try to analyze a little bit what this equation means, and let's make sure that it makes sense. Okay, so since this is a positive amount, then this means that the stress, the change of stress is going to depend on the change of temperature with the same sign. For example, if I inject a cold fluid that decreases the temperature, then this is going to cause also a decrease in the horizontal stress. If I inject a fluid that causes an increase of temperature, then this is going to cause an increase in the horizontal stress. And that makes sense, because with the cold fluid, the rock will tend to shrink on horizontal direction, but it can't. So instead, there is a thermal stress relaxation. There is a decrease in stress. On the opposite, if I were to inject a hot fluid, then the rock will try to dilate, but it wouldn't be able to do that. So instead, there will be an increase of the effective horizontal stress. And just as a reference, let's come back over here and remember our problem. Our problem and our equation was meant to calculate the increase of effective horizontal stress in this continuous formation, in which I have no possibility of having horizontal strains. So as a result, I have changes of stresses. And the parameter that predicts those changes of stresses are this combined parameter that combines the linear thermal dilation coefficient beta, the Young modulus, and the Poisson ratio. Okay, before putting some numbers and just making running an example about this, let me just remind you something that it is important to keep in mind in order to also read these equations. And I'm going to add this over here. If you remember that when we just considered strain and deformation and just mechanics, we calculated that the effective horizontal stress, sigma 1,1, depends on the effective vertical stress through the effective lateral stress coefficient, which for linear elasticity depends on the Poisson ratio. That is our starting value. If we have a change of pore pressure, we saw that with the theory of elasticity, we could predict what that change of horizontal stress would be as a function of the change in pore pressure, and this one will be equal to alpha. Let me actually be a little more precise. In this case, we were calculating the total stress. This was a function of the Biot coefficient and also a function of the Poisson ratio. And last, now we see that for a change of temperature, the coefficient that tells us what is the variation of stress with temperature is equal to this parameter beta E 1 minus Poisson ratio. So now we expanded just our mechanical equations with changes of temperature and changes of pore pressure and changes of temperature. And now we see that with the new physics that we have for the case of pore elasticity, here we have the Biot coefficient. For the case of temperature, now we have the linear thermal dilation parameter. Okay, so just to have an idea about the importance and the magnitude of these stresses, let's do something similar to what we did before. Let's just assume some typical values, like for example, a beta equal to 10 to the minus 5, 1 over a degree Kelvin. Let's assume a rock with a Young modulus of 10 gigapascals and a Poisson ratio equal to 0.2. If I use all of these parameters, I can calculate that the change of horizontal stress due to a change of temperature is going to be equal to 0.1 MPa per degree Kelvin. So if I change, for example, the temperature 10 degrees Kelvin or 10 degrees C, which is more or less 20 degree F, I would have a change of horizontal stress of 10 megapascals under these conditions. And that's quite a large stress. 10 megapascal is more or less 1500 psi. And you can see that now these changes of stress caused by temperature can be quite important, and they should not be neglected in applications in which we inject a fluid which has a temperature which is significantly different than the temperature of the formation. In this particular case, we have assumed a case which is one extreme of the problem in which the entire layer cools down. Usually what we see in real problems is that the region that cools down, it's limited to the neighborhood of the wellbore. And let me show one example about this. So I think, let me see if I missed something over here, but I don't think so. We developed all the equations. We found what is the parameter that tells us what is the change of the stress with change of temperature. I think that's everything. So let me share this example that I have over here with you. And here I have a paper that I recently published with two collaborators, in which we look at what would be the response of an injector running a step rate test to the injection of carbon dioxide at ambient conditions. Basically, what we wanted to study was if we will expect any change in the step rate test, adding the condition of temperature. And this is something that it is already known to happen, but not that well constrained for the case of carbon dioxide, and in particular for this case that we in which we did a field study. And so then the objective was to calculate and to simulate what would be the response of the pressure as a function of the injection schedule, and also for a temperature of injection that was lower than the temperature of the formation. And let me tell you what, let me show you what the results are. The first thing that we do is we build a one-dimensional mechanical layer model with the properties of the formation, the wave velocity, something that we have already seen in this class, in order to build a profile of the minimum horizontal stress, also considering poroelasticity. And after that, we do a simulation in which we inject the fluid in this formation, which is heterogeneous in vertical direction. So here is an example of the model and what the prediction of the minimum horizontal stress is, here in green, and what was adopted in the model here in red. And basically what we see is that as we inject the fluid, in this case carbon dioxide, we see a different response whether we're considering thermo-elasticity or not. If you wouldn't consider thermo-elasticity and you wouldn't consider the stress relaxation in horizontal direction as expected, you would predict that the pressure at injector is proportional to the rate. However, in this case, including the presence of thermo-elasticity, we saw that the pressure at injector would not be as high as predicted without accounting for thermo-elasticity, but will be a little bit lower. Why? Because at more or less this time, we predict that the effective stress will go to zero, and that will produce the creation of a fracture. And the creation of that fracture would inhibit a further increase of pressure. And this is what you see in this plot as well, in which actually the fracture starts earlier, but it gets just very large at around this time, and in which the effect of thermal stress relaxation produces a change of horizontal stress near the injector of several megapascals. And this is combining the effects of poroelasticity and thermoelasticity. So this is just one with poroelasticity, this one is with thermoelasticity. And what we see, however, is that although the injection of the cold fluid prompts an earlier initiation of a hydraulic fracture in this case, that that fracture is pretty much restricted to the zone of the injection and to the areas where the minimum horizontal stress was the lowest. And also we see that the front of change of temperature is a lot smaller than the front of the change of CO2 saturation. So that means that the CO2, injected CO2, reach a lot further into the formation, and the temperature for at the same time was just restricted to the region of the wellbore. Of course, if you were to inject for a, a longer amount of time, and if you were to reach steady state conditions, then your change of temperature would tend to increase over a larger reservoir area, and that would produce a larger decrease in temperature too. Okay, so there is one more plot that I'd like to share with you. Here we have a sensitivity study, but I like this plot as well, where for typical parameters also we predict the influence of the thermal stress change due to the change of temperature. And for this particular case, we had a change of temperature of about 50 degrees. And 50 degrees, it's a quite considerable change of temperature. And we expect a change of stress in the order of 5 to 10 megapascals. Remember, 10 megapascal is about 1500 psi. But there are some other cases, however, in which the changes of temperature could be a lot larger than that. Like, for example, in this particular case, also with injection with CO2 in a Nordic region, the change of temperature between surface and the reservoir was about 90 degrees. Of course, as the fluids get into the reservoir, they heat up slowly, but if your injection rates are considerably large, you will not have enough time for that fluid to change temperature to get to something closer to the reservoir, and you may expect a considerable decrease in effective horizontal stress and also on total horizontal stress when you add the poroelastic part as well. Okay, so I'm gonna provide a link about this paper in the YouTube video. There is one more thing that I like that we discuss for this lecture, and it is to talk about the changes of stresses around a wellbore. And okay, here's my mouse. This is going to be something very similar. Changes of stresses due to temperature around the wellbore. Okay, so in this case, what we want to solve is what is going to be the change of stress around a wellbore. Oh, let me put this closer to the center. Around the wellbore, in which I have far field stresses, for example, sigma 1 and sigma 2, where sigma 1 and sigma 2 are principal stresses, and sigma 1 is larger than sigma 2. The solution for this problem is, let me just write the equations, is sigma theta theta for R equal to A is equal to the pressure in the wellbore minus the pore pressure in the formation minus sigma 1 plus 3 sigma 2 plus the component of the thermal stress sigma theta theta T. And let me explain a little bit for this equation. And here, for theta, if this is the center of the wellbore, and this line aligns with the direction of the largest principal stress, then if I have an element somewhere around the wellbore here, theta is going to be the angle to that element from the direction of the maximum principal stress, and R is going to be, let me do it with another color. Okay, so this is going to be theta, and this is going to be R, where I have a radius of the wellbore equal to A. So, okay, now I understand my equation. With this coordinate system, I can calculate what the stresses around the wellbore are, and for this is going to depend where you are around the wellbore, and the equation for sigma theta theta and sigma RR, you can find them here in my notes in section, let me move this over here. Section is actually the entire chapter 3 about wellbore stability, and here if you go to the Kirsch solution, you will find a development of all those stresses. And finally, here you will have the equation of sigma theta theta as a function of theta, that now what we're doing is just writing the solution at theta equal to 0 and at theta equal to pi over 2. And those are going to be, again, you can go here to my notes to see the full solution, but let me come back to my OneNote. And this is where my mistake was before. This is going to be the solution for sigma theta theta at R equal to A. And in this case, this is going to be at theta equal to 0. The Kirsch equation tells me that the stress at such position where theta equal to 0 is going to be, let's use here, point number 1, where this is going to be an element here. And the stress at that point is going to be a function of the mud pressure or wellbore pressure applied on the wall of the wellbore minus the pore pressure in the formation in the pore space minus sigma 1, which is the maximum horizontal stress, plus 3 times sigma 2, which in this case is the minimum horizontal stress, plus the thermal stress. This part, let me emphasize that just comes from the Kirsch equation. And again, if you want to see that in detail, please go to my notes. And this is the part of the thermal stress, which is the new thing that we are adding within this chapter. And let me just complete the equation, because at this point, what you would expect is that you're going to have the lowest hoop stress possible, where hoop stress is sigma theta theta. The other equation is for position number 2, and here in position number 2, the equation is going to be very similar, but the part of the Kirsch equation is going to change. So if this is 90 degrees, then this part remains the same, but now this part is going to be 3 sigma 1 minus sigma 2 plus the thermal component. All right, so let's first think about just the part of mechanics. According to the Kirsch equation, if I have my maximum stress going in this direction with sigma 1 larger than sigma 2, that means that at these points in position 2, I'm going to have more compression in hoop direction than in this direction. Why? You could imagine this as an arching effect, where the stresses go in this direction and have to bend around the cavity and go into the other side, right? And if this one is larger than that one, then I'm going to have more compression, the hoop stress in this direction than in that one. Imagine that sigma 2 is equal to 0. If that's the case, then the hoop stress at this position is going to be equal to 3 times sigma 1. And actually the hoop stress at this position, since here sigma 2 is going to be equal to 0, let's imagine for the moment that this one is equal to 0 too, is going to be a tension. So this area is going to be the area of the wellbore that has the lowest hoop stress from all the possible solutions around the wellbore. So if there is any fracture, in this case, it is going to be here. And let me do the schematic of this fracture. This fracture will happen here and there. And this fracture is going to happen whenever sigma theta theta effective gets smaller than the tensile strength of the rock. Okay, so this is just due to the mechanics. Now with the thermal stress, I can also cause more tensile stress or more stress relaxation because I'm cooling the rock. If I have a drilling mud that has a lower temperature than the formation itself, I'm going to produce a thermal stress relaxation in the tangential direction or the hoop stress. And the derivation of that is very similar to what we have done before, and we're not going to repeat it, but actually the equation is the same. The change, but now is of hoop stress due to temperature in this equation is going to be equal to beta times the Young modulus 1 minus Poisson ratio times the change of temperature, that since we are already using theta here, don't get confused, the theta here doesn't mean temperature, means the angle which is shown here. Let's just put delta t. And this one, this additional thermal stress term is going to tell you how much the hoop stress is going to change due to a change of temperature. And let me do one more thing that hopefully is going to clarify also what is going on in here. Let's plot the hoop stress as a function of the angle theta around the wellbore, where this is 180 and this is 360 degrees. All right, so according to this equation that I have over here, if I have just the Kirch component at theta equal to 0, let's imagine that I have a mild compression somewhere over here. At theta equal to 90 degrees, I'm going to have the highest compression, let's say a point over here, and back at 180 degrees, I'm going to have this mild compression, and again, high compression, mild compression. If you take a look, let's come back quickly to these equations, you see that there is a cosine here. So actually, we are going to have a sinusoidal shape here that is going to look like this. And this plot is telling you what is the variation of the hoop stress around the wall of the wellbore, just taking into account mechanics, and what I mean is just part of the Kirsch equation with the mechanics only. If you add the thermal component, and if we assume also a cooling temperature with delta T decreasing, what I could cause is a change of the hoop stress, which is going to happen everywhere around the wellbore. And this change could cause for example, the rock to get into tension. This is due to a decrease in temperature. Okay. Here, what I have also assumed is that we have a steady state solution. Let me add that because it's important. It doesn't require that your temperature is the same everywhere in the formation, but as long as you reach a steady state solution and the temperature everywhere around the rock is the same, this is going to be the answer for that additional thermal stress. Okay, so we have seen that we can apply this concept of thermo-elasticity and this extension to thermo-elasticity of problems of reservoir geomechanics, calculating the change of temperature in a formation, and we can also apply this problem to drilling. And this is actually quite important because sometimes you can just fracture a wellbore due to a change of temperature. In the following lecture, what we're going to do is we're going to extend the thermoelasticity equations to a general problem and look at the temperature diffusivity equation, and then to talk about the coupling of temperature with pore pressure in the theory of thermoporoelasticity.